Hey everyone, this is Dr. Walker. In this video, we're going to go over an example from v513 electric flux concept. For now, we're sticking to uniform electric fields and flat surfaces. In this example, we want to find a flux through a cube. We have a field directed in the x direction, and the cube has length L. Now, technically, this is a closed surface, which we will go over in the next video, and that's why there's all these little dA's instead of just calling this A, but that's okay. We can just ignore the little dA's for now. The process is going to be the same that we just learned in video 513. To find the net flux through this cube, we can just find the flux through each surface and add them up. We don't have to worry about the fact that this is a closed surface. Okay, so how do we do this? Well, remember that the electric field has to have some component perpendicular to the surface. So if you think about this top surface, A3 for instance, the electric field is parallel to that surface. So that means that there is no flux through surface 3. The bottom surface 4 either has no flux going through it because the field is parallel to that surface. What about this front surface here? Doesn't have a number, but the field is parallel to the surface because this surface is parallel to the xy plane. The field is in the xy plane. Likewise, the back surface has no flux. So that means that we only have electric flux through this area 1 over here and the area 2 on the right. So to find the net electric flux, we're going to find a flux through area 1 and a flux through area 2. Because the electric field is already perpendicular to the surface, then that's going to really simplify things when we write the dot product E dot A. Let's go ahead and write it, plus E dot A2 here. Then we see our angle for A1, so A1 is pointing to the left. We can just call it A1 here. And it's 180 degrees from E, which is pointing to the right. So we have E, and the area is just A, right? They all have the same area because they're a cube. So EA cosine of 180, and then for the flux number 2 here, we have EA, and this time A is pointing to the right, just like E, the angle is 0. So what we get here, and the area is the area of a face, which is L squared. So we get negative EL squared plus EL squared. So we actually get a net flux of 0. And this is going to be significant once we get to Gauss's law pretty soon, in a couple of videos from now. So let's do a second part to this example. What if instead the field is given by this expression 5 I hat minus 6 j hat? So the field is still uniform, but instead of pointing horizontally, it points somewhere down. It's in the xy plane pointing down. And for this part, we just want to find a flux through surface 3. So we can draw A3 pointing upward perpendicular from surface 3. And we can see that the field does enter the surface. There is part of it that is perpendicular to the surface. All right, so let's go ahead and write down what we know, that the flux, the electric flux, is going to be E dot A3. And remember how the area vector is defined, right? The area vector is defined as a vector that has a magnitude equal to the area, but a direction equal to the unit vector, right? N is the unit vector perpendicular to the area. In this case, it's in the y direction, which is j hat. So the area vector in this case, the area is L squared, and the direction is going to be j hat. So we are looking for the dot product of 5 I hat minus 6 j hat, that's our E, and we're going to dot it with A. Now A doesn't have an x component, but let's just write 0 for the x component, the I direction, and then L squared j hat. So we're doing E dot A, and if you remember how to do a dot product, you add up the x components, you add up the y components. If you had z components, you'd add those up and you just add them all together. First you multiply them. Sorry, if I said add, I meant you multiply those components, you multiply these components, you multiply the other, and then you add those products together. So we have 5 times 0 plus -6 times L squared plus 0. So our final answer is -6L squared, and the units would be newtons meters squared per coulomb. We notice that for this final answer here, we notice that the flux is negative, and that is because the field is entering the surface, and we'll actually see that more in the next video once we talk about closed surfaces.